Hello, and welcome again to another series of lectures on functional analysis. So we start with a new chapter on linear operators. As a motivation, let us consider some examples of linear differential equations that has been stated at the beginning of the course. So the simplest would be, let's say, a system of ODEs. You have a system of linear ordinary differential equations, and let's say we have the following: u prime plus m of t, some matrix valued function m of t, u of t equal to f of t. And with an initial data, which we do not specify at this point. So here, the given functions are m, let's say from 0 to t. So t equal to 0, you can think of this as your initial time, and capital T would be your final time. So this is a matrix valued function, and also a given right-hand side f, which you can think of an external force or source of your ODE. And m describes the dynamics of your differential equation. And an unknown vector u that you would like to determine. So in the previous lectures, we have discussed several, let's say, function spaces. For instance, you can look at this. You can think of Holder spaces, your Lebesgue spaces, or your Sobolev spaces, having weak derivatives. So the significance of these function spaces is that this is the vector space or your set of solutions. Vector space where solutions are located. So this is your set where you look for your solution. Okay, so for this ODE, suppose that at this point, suppose that I take u to be in some function space x. Okay, which we do not specify at this point. So let us suppose that you have a function space and you choose this vector space as your solution space. Suppose we want to look for u in this function space x, and we let us define, let's say, an operator a from x to y for some function space y, which is again not important at this point, and f is located in this function space. So the definition of A would be this differential operator. So this would be, let's say, the action would be AU. This is defined to be A prime plus M times U. So this is an example of what we call a differential operator. And with this, we can you rewrite this ordinary differential equation as the following linear system. So here we now have, let's say, so the right hand or the left hand side would be A. Let us write this as star. So this can be written as the following equation. AU equals F. So here we have, let's say, an infinite dimensional linear system. Here the function space would be both infinite dimensional. So x and y would be, let's say, infinite dimensional function spaces. Okay, although the values, of course, here of your unknown function and the source function are finite dimensional, since they lie on the Euclidean space Rn, your function space can be infinite dimensional. So for instance, you can think of the space of continuous functions or continuously differentiable functions. They're infinite dimensional. So we have rewritten or recasted our system of ODEs as an infinite dimensional linear system in infinite dimensional function spaces. So as I said at the beginning of the course, you can think of functional analysis as an infinite dimensional linear algebra, or a subset of that. So, and in this way, so finding for you, it is enough to consider, let's say, so for existence of a solution, it is enough to consider that A is surjective. And for uniqueness, so suppose you have two solutions, you subtract that and you will see that you need that A is injective. So if you have a solution, it is unique if your operator is injective. So in particular, you have a unique solution if your operator A is bijective. Okay, and this A here is a linear operator. So this is the scenario where linear operators can appear. Okay, so you can think of the function spaces that we have discussed to be the function spaces or the vector spaces where the solutions are solved. Okay, and if you want to translate the system of ODEs, you can write it with respect to some linear operator as an infinite dimensional linear system. So you can think of A as loosely speaking, an infinite dimensional matrix here. And you want to solve this linear system. And for existence and uniqueness, you need that A is both surjective and injective. And as another motivation, let us consider the Poisson equation. And to set up the problem, suppose I have a bounded domain in R squared or Rn, let's say, okay, and this is smooth. By that, let's say the boundary is smooth. And let's say this is also bounded. So suppose this is your bounded domain omega, and this is the boundary. And you can think of, let's say, you have some sort of a temperature distribution. So think of a solid body, and in this solid, you have a temperature at a particular point, let's say x. So let's say U of x would be the temperature at the point x in omega. So at a given point, we suppose that we have an assigned temperature. Of course, here we assume that the object or the material is a continuum. So that we can apply the classical methods of continuum physics. So take note that here you have, let's say, a material, a solid body, for instance. It consists of what? A finite, okay, finitely many number of atoms or molecules. And you can, of course, only assign a temperature on those molecules. So here you have finitely many discrete temperature values. However, that would be an intractable problem. So what we assume is that the material is a continuous body, wherein at each point of the domain, you can assign a temperature field at that point. Okay, so this is a common assumption in continuum physics. Suppose we have, let's say, the unknown temperature distribution, say U, defined on points in omega with values in R. Okay, so temperature must be, of course, positive or non-negative, but here we can think of U as some sort of a scaled temperature, so that you can assign real valued temperatures as well. So let's say this is some sort of a scaled or translated temperature, to be precise. So the governing equation would be, let's say, the following. So negative Laplacian U of x equal to f of x, or x in omega, with some boundary condition, which we do not specify at this point. Okay. So this is your Laplace operator, or Laplacian. This would be your, let's say, heat source. So here we are talking about stationary heat sources, and so the derivative with respect to time would be 0. So let's write it down. So we have a stationary heat problem. Therefore, no changes in time appears here. And of course, there are constants here. For instance, we should have, let's say, some sort of a negative kappa, where kappa is the thermal conductivity. This signifies how, let's say, fast is or how slow the diffusion of temperature. Again, let us define, let's say, U given some heat source F in some function space Y. We look for a temperature distribution in some function space X. So again, here, X and Y are some function spaces. And we define, so the problem can be written as, let's say, A of U equals F, where A here is a linear operator from X to Y, defined as follows. So negative A, so A is negative kappa Laplacian. So AU is negative kappa Laplacian U. And those who are not familiar with the Laplacian, this is just the trace of the Hessian. So this is the sum of the second order, of the following second order partial derivatives. So squared d squared u over d xn squared. So again, we have written this stationary heat problem as some sort of similar to a matrix equation. AU equals F. So that is the common theme of these systems. Well, you can generalize this into, let's say, the stationary heat problem. And now you have the time derivative, and your function is now dependent on time, and as well as your heat source. So let's say for some time between 0 to t and x in your smooth domain omega, with, again, boundary. And since you now have a time-dependent problem, we also need to impose boundary, or I should say initial conditions. So, which we do not specify again for simplicity of discussion. Because here we're just aiming at or giving the main ideas. So again, for some, so given f and y, again in some function space y, well, let's say it can be this is different from the y provided in the stationary problem. We want to seek a space u, a u in some space x. So in this function spaces xy, such that AU is equal to F. where our operator A now, defined from x into y, is defined by AU. So you just take the operator on the left-hand side. And with this, your stationary heat problem can be recasted again as a linear system in infinite dimensional function spaces. Since our problem is time dependent, these function spaces, well, based on the theory, can be taken as the Bochner spaces or the Sobolev-Bochner spaces. Again, going back to our 3 examples, a system of ODEs given by this problem can be written as an infinite dimensional linear system, as well as the Poisson equation. And in which case, if your heat source is 0, your functions U are called analytic functions, which appears in the study of functions of complex variable. Okay, so this appears if f is 0, this type of equations appear in complex analysis. And finally, for the stationary heat equation, you can also write this as an infinite dimensional linear system. So as an analogy, think of your function spaces as your Euclidean spaces, and think of your linear operators or linear differential operators as your system matrices. So the main idea, or the rough idea in studying linear differential equations, specifically in asking whether you have a well-posed problem, in particular the existence and uniqueness of solutions, you can rewrite such problems as infinite dimensional linear systems on appropriate function spaces. Again, the function spaces are the sets wherein the solutions are sought, and the linear differential operators as your infinite dimensional matrices. So that's the motivation for linear operators. In the next lecture, we will discuss a specific type of linear operators, and these are the bounded linear operators.